When we charge a capacitor, we force electrons to migrate from one plate to the other, separating positive and negative charges. Where exactly does the energy from this effort go? As charges accumulate, they create a strong electric field spanning the gap. Instead of being absorbed by the metal, energy stays trapped within the tension of the field itself. To understand a capacitor, we have to look past the physical hardware and focus entirely on that invisible field. Charging requires physical work. As a battery pushes charges onto the plates, the growing electric field pushes back. We calculate total work by integrating voltage with respect to charge, instantaneous lowercase q up to the final capacity uppercase Q. This integral resolves into three stored energy formulas: q squared over 2c, 1/2 qv, and 1/2 cv squared. Each of these equations quantifies the exact same physical reality: the total potential energy locked within the electric field, ready to be deployed. This gap in the math reveals a constraint. A battery provides total energy equal to CV squared, yet the stored energy only accounts for half that amount. When charging an uncharged capacitor, that missing 50% of the work is lost to the surroundings as heat. This 50% loss is a physical law of thermodynamics, dictated by the mechanics of charging from a constant voltage source. Focusing on the field itself allows us to measure the concentration of energy, or energy density. This is defined as 1/2 epsilon naught times the electric field squared. Let's apply this. Imagine a mechanical arm pulling the plates further apart while the battery remains connected to the circuit. Pause the video here. Using the formula U equals 1/2 CV squared, predict whether the total stored energy increases, decreases, or stays the same. Because the battery is connected, the voltage remains constant. Since pulling the plates apart increases the distance between them, the capacitance decreases. With a constant V and a dropping C, the total stored energy must decrease. This establishes a priority for solving capacitor problems. You must first identify which variable the environment is forcing to remain constant. Engineering requirements for devices like defibrillators or motherboards demand high capacitance in small spaces. We solve this by inserting a dielectric material, which multiplies the capacitance by a factor of K. If the battery is connected, the voltage stays constant, and the dielectric causes the stored energy to increase proportionally with K. However, if we remove the battery first, the charge becomes trapped. With Q constant, the increased capacitance now sits in the denominator of our equation, causing the total stored energy to decrease. Dielectrics allow for efficient miniaturization, though their effect on energy is entirely determined by whether the system is open or closed. This summary organizes the derivations. On the left are the macroscopic hardware formulas for total energy. On the right is the microscopic formula for energy density. Mastering these circuits means looking past the components to see exactly where and how electrical energy lives in the physical world. Engineering requirements for devices like defibrillators or motherboards demand high capacitance in small spaces. A dielectric multiplies capacitance by K. If the battery remains connected, voltage is constant, and stored energy increases with K. However, removing the battery traps the charge. With Q constant, the larger capacitance is now in the denominator, so total stored energy decreases. Dielectrics allow for efficient miniaturization, though their effect on energy is entirely determined by whether the system is open or closed. This summary organizes the derivations. On the left are the macroscopic hardware formulas for total energy. On the right is the microscopic formula for energy density. Mastering these circuits means looking past the components to see exactly where and how electrical energy lives in the physical world.